Welcome to my talk about sliced optimal transport sampling. In this talk we will talk about sampling, especially in the case of Monte Carlo integration. So what is Monte Carlo integration? Let's say you have a function you do not know how to integrate and you want to compute its integral. Well, Monte Carlo integration says you just take random sampling points and you average a function value at those points. And then you get an approximation of your integral. This approximation converges in speed 1 over square root of n. And what you may ask yourself is this possible to improve our convergence rate? Like, you see there are some points that are clustered and there are some holes in the points. Is it possible to spread them more in order to get more information? Well, yes it is, and that's what we are going to talk about. Oh, and by the way, rendering has been shown to be just computing this huge integral in high dimensions. And so it's mainly Monte Carlo integration. What we will present in this talk is an optimal transport-based energy minimization that generates high-dimensional samples uniformly. Plus we add some rendering specific method that we will talk about later on. So let's talk a bit about samplers. So white noise sampling, so that is pure stochastic sampling that works in any dimension but has a really slow convergence rate. Then we have low discrepancy and optimized low discrepancy samplers. They work in pretty much any dimension and have a great convergence rate, but they sometimes generate some artifacts because of their alignments. Then we have Poisson sampling that is difficult to compute in higher dimensions and that doesn't converge that fast. And then we have blue noise sampling, that is the kind of sampler we are trying to make. And they usually have a quite fast convergence rate, but since they are based on optimal transport, and as we will see, it's complicated to compute, they do not go that high in dimensions. When you see samplers, you may ask, are there some theoretical tool you can use to measure the quality of a sampler? Well, the main tool people use is discrepancy. And that is based on computing the difference between the expected distribution and the effective distribution you get. What they do is they take the maximum for all convex shapes of the difference between the number of points expected in the convex shape, so their area, and the number of points there is effectively. On the right you can see there is the blue convex shape that has 3 points in it while being 1/4 of the domain size, and so we expected 2 points. That gives us a discrepancy of 1/8. What makes discrepancy such an interesting quality measure is that it's directly linked to the integration error. Another quality measure you may use is optimal transport. Optimal transport is just computing a distance between two probability distributions by computing how far you have to displace one to get to the other. This also works for discrete distributions. Optimal transport is, as I said, a quality measure, and that is given thanks to Kantorowicz-Rubinstein that bounds the integration error by the transport cost of your points onto a uniform distribution. So, since optimal transport is a good quality measure, generating a point set that minimizes optimal transport might be a good idea. The problem is there is no fast algorithm to minimize optimal transport in higher dimensions. But let's talk a bit about one-dimensional. It's quite easy to compute optimal transport in one dimension. Let's say we have 3 points and we want to compute the transport cost to a uniform measure on the pink line. Well, what we would do is just you solve the points, you split your integral into equal parts, And then you just take the first point that you map onto the first part, and then the second point onto the second part, and the third point onto the third part. And that's it. You've computed optimal transport in one dimension. This ease to compute optimal transport in one dimension led to a new definition of optimal transport, the sliced optimal transport. That is the integral along all directions of the one-dimensional optimal transport between the projections of our distributions. And this integral can be estimated through Monte Carlo. That is linear in the dimension, and so that can be used in higher dimensions than what usual optimal transport does. So let's say now you want to minimize optimal transport. What you could do would be take a direction and then minimize optimal transport along this direction. And then you take another direction and you minimize optimal transport along this other direction. And then you iterate until you get convergence. Until now, we just talked about generating points onto a cube. But when you go to higher dimensions, projecting a cube onto a direction gets increasingly harder because the number of vertices your cube has is exponential in the dimension. What we did was we worked on a spherical distribution instead of a cubic distribution. But to do this, we need to map our final points to the cube. So here you can see in 2D the mapping between our points. That is just Shirley-Chiu. But you need the same in higher dimensions. And so you would be looking for a volume preserving with low distortion mapping. The main part of the work was made in Grip and Trog in 2008, where they introduced a formula to solve to get a mapping between the n-dimensional ball and the n-dimensional cylinder. And then once you have this mapping, you can just recursively use it to map the cylinder to the cube, since the projection of the cylinder is just a n-1 ball. In practice, what we do is more complicated than what I showed just before. Instead of taking just one direction, we have to take a full batch of directions. And then we solve optimal transport along all those directions. And we use this solve to compute in which direction to move our points to minimize sliced optimal transport. And then we iterate until convergence. And when we like the points, we just map them to the square. Here is a video of how our points converge. So you can see it's quite fast in the beginning, and then we have a lot of oscillation until we reach an optimum. The algorithm I showed is based on two different parameters. There is first the number of directions we take in each slide. Here on the left you can see a plot of the optimal transport cost based on the batch size. And as you can see, there is not much variation depending on the dimension. So what we did was just take 32 slices in whichever dimension we work. So here on the right, you can see the plot of the transport cost depending on the number of iterations. And as you can see, the number of iterations needed before convergence increases with the dimension. So what we did was just take around 4K for 2D points and then take 60K iterations for 20D points. But it doesn't grow much higher. We then use our points to integrate analytical functions in 6 dimensions. So here on the left you have Gaussian's integration, and on the right you have discontinuities integration. So on smooth functions we see that our points lead to a good integration and that we outperform most common samplers up to 60K samples. But on the right, on the discontinuous functions, we see that up from 1K points, we are outperformed by the usual samplers, even though we outperformed them before that. To use our samples in rendering, we still need an additional property. When you do rendering, you use your two first dimensions, here x and y, to sample the screen space. And then you use the next two dimensions to sample the first bounce direction. And then you use the two last ones to sample the light. Well, you have a need for projective uniformity in this case, because you want your points to be uniform in high dimensions, but you also want the points you choose on the surface of your light source to be uniformly spread. So here you can see the difference between rendering without projective uniformity and with projective uniformity. On the error map, you can see that there is much more red on the top than on the bottom. As we rely on Monte Carlo integration, we can bias our direction distribution to enforce this projective property. Once we added this property, we tried using our points to render different scenes. So here you can see against several samplers that we perform quite well up to 1k points, and then we kind of lose our edge. And then here you can see it with rank 1. So at 32 samples per pixels, we outperform rank 1. But when we reach 1k sample per pixel, we sometimes outperform and sometimes fall behind. So this is kind of like with the analytical integrals we showed before. And of course, there are many more different scenes we show in our paper, including a volumetric one. The last thing our sampler allows us to do is multi-class sampling. So multi-class sampling is when you want points to be uniform, but at the same time you want to be able to extract just some points and you want them to still be uniform. And so there is a way to do it with our method that we explain in our paper. As a conclusion, I would like to say that we showed that optimal transport is relevant to Monte Carlo integration, and that sliced optimal transport is an efficient way to compute it and to minimize it. And our method is valid for basic Monte Carlo integration, and we added some method to make it relevant for specific applications like rendering. Some work that remains to be done is exploring the use of sliced optimal transport for different kind of sampling applications, like for optimizing another sampler than ours. Plus, we saw that discrepancy and sliced optimal transport have different qualities, and maybe there is a quality measure that mixes both of them and gives good results. Oh, and the code for our work is available on GitHub, or you can flash this QR code. Thank you for listening to me, and if you have any question, see you next week.